So we showed previously that the Maclaurin series of f of x equals e to the x is the series x to the n over n factorial. So one question we might ask is, for what values of x does this series converge? So we can try and find its interval and radius of convergence. So for that, we'll just apply the ratio test like we normally would in any power series. And let's see what would happen in this case. So we'll do an plus 1, which is going to be x to the n plus 1 over n plus 1 factorial. And then the reciprocal of an, which will be n factorial over x to the n. If I simplify this, I know that, for instance, here the n factorial will divide with the n factorial down here, because this is n plus 1 times n factorial. And then here x to the n divides with x to the n up here, leaving me with just one factor of x left over. So in fact now I'll just write the absolute value of x over n plus 1, which as n goes to infinity, this will always just be 0. So it's less than 1 regardless of what value of x we choose. So therefore it's convergent for all x. Now the question is, if we know it's convergent for all x, what exactly does it converge to? And since we've kind of shown that with the Taylor polynomials, the values of the Taylor polynomials tend to approach the graph of e to the x. So if we were to add up infinitely many terms of the Taylor series, would it always converge to the values of e to the x? And let's figure out how we can prove that. So one important tool will be to use Taylor's inequality. So Taylor's inequality gives us a way of finding a bound on the remainder term. It says that if I have a bound on the n plus 1th derivative of x, so if we know that that's less than or equal to m, some value m, for all x within an interval around a, then the remainder Rn of the Taylor series satisfies the inequality. Rn of x is less than or equal to m over n plus 1 factorial times x minus a to the n minus 1. And this is for the same range around the point A. Okay, so we can use Taylor's inequality here to kind of answer a couple of analytical questions we might have about Taylor series. For instance, how accurate is it? How good of an approximation is it when I do a partial sum, because it tells us something about the error, right? But here we can also use it to show that as n goes to infinity, Rn goes to 0, which essentially tells us that the Taylor polynomials will converge to the values of f as n goes to infinity. So one useful, when we're using Taylor's inequality, one useful fact that will come in handy is if I'm taking the limit as n goes to infinity of x to the n over n factorial, this will always equal to 0 for any x. And that's just because n factorial will grow much more rapidly than x to the n. Essentially, factorials are going to grow more rapidly than any power function could. And so let's now prove that e to the x is equal to the sum of its Maclaurin series. All right, so here our goal is to show that Rn of x goes to 0 as n goes to infinity. Well, according to Taylor's theorem, we know that the absolute value of Rn of x is less than or equal to m over n plus 1 factorial times x minus a, in this case a would be 0 because it's a Maclaurin series, to the n plus 1, where m is an upper bound for the n plus 1th derivative at 0 in this case, for values of x that are in an interval of length d. Well, we know that for the function e to the x, and I shouldn't use 0 here, I should use x. Anyway, so we know that for e to the x, its derivatives are always e to the x. So we want to find m such that the n plus 1th derivative at x, which is e to the x, is less than or equal to m for all x less than or equal to d, an absolute value. And we know that, okay, well, the biggest e to the x will be at the biggest value of x, because it's an increasing function. So we know e to the x will be less than or equal to e to the d for these x. So we'll use e to the d for m. So here we've shown that Rn of x must be less than or equal to e to the d over n plus 1 factorial absolute value of x to the n plus 1. So now if I take the limit as n goes to infinity of the absolute value of Rn of x, well, this would be less than or equal to the limit as n goes to infinity e to the d over n plus 1 factorial absolute value of x to the n plus 1. E to the d is just some constant that you can pull out of the limit. So if I'm taking the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, well, we know from what I was mentioning in the previous slide that, yeah, factorials are going to grow much more rapidly than power functions as n goes to infinity, so this is going to go to 0. And that proves that the limit as n goes to infinity of Rn is equal to 0. Okay, so basically what we've shown is that e to the x is going to be the sum of its Taylor series, of its Maclaurin series. So we've shown that e to the x is the sum of this series x to the n over n factorial. So we know that for any value of x that I choose, this series will converge to the values of e to the x. And in particular, if, for instance here, if I let x equal to 1, then I get the Taylor series, 1 over n factorial, really converges to the value of e. So here's just one way I can represent the number e, in this case as an infinite series. So we know 1 over n factorial, the series 1 over n factorial will converge to e. Now let's suppose I want to find the Taylor series for f of x equals e to the x at a equals 2. Well, let's write out what that would be in terms of the formula. So we know the Taylor series for any function centered at 2 would be of the form f of 2 plus f prime of 2 over 1 factorial times x minus 2. And then plus f double prime of 2 over 2 factorial x minus 2 squared. F triple prime 2 over 3 factorial x minus 2 cubed, and so on, right? So we can continue generating infinitely many terms this way, but let's see if there's a pattern that we can recognize, that we can just write the formula for it. And the nice thing again about e to the x is that we know all the derivatives of e to the x are all going to be the same. They're all going to be e to the x. So any ordered derivative will always be the same. So therefore the nth derivative at 2 will always be e squared for all x. I'm sorry, for all n. So any ordered derivative will always have the same value, e squared. So we know all these values here will be e squared. So this will be e squared, this will be e squared, this will be e squared, and so on. This will be e squared, this will be e squared. Okay, so we can just fill in e squared for all those values in the formula. So here, writing it in summation notation, we have it's going to just be e squared over n factorial x minus 2 to the n, and going from 0 to infinity. Okay. Now what's a little bit strange about this is that you need the value of e squared to get an approximation for e to the x. So this is probably not the best way to approximate the values of e to the x if I need a value of e squared in order to do it. So maybe there's a better way to do it, and maybe just doing it at a different center might be more useful. Anyways, so what about a different function? How would I find the Maclaurin series for sine x? And in this case, again, we want to prove that it represents sine x for all x. And sine x, again, is nice because it has easy derivatives. So let's just kind of list out a few derivatives. We know the first derivative is cosine x. Second derivative is the derivative of cosine is negative sine. Third derivative is negative cosine. Then the fourth derivative actually brings me back to the original f, which is sine x. And then it cycles through these values over and over again, right? So this would be the same as the fourth derivative, fifth derivative, sixth derivative, seventh derivative, and cycles through these four values over and over again. So let's just go through these values here and evaluate each of them at 0. So we know sine of 0 is 0. F prime of 0, which is cosine of 0, is 1. F double prime of 0, which is negative sine of 0, is 0. And then the third derivative at 0, which is negative cosine of 0, is negative 1. Now if I write out the Maclaurin series, so remember we're using these derivatives again because in our Maclaurin series formula we need those values. And in this case, let's fill them in our formula, and we can see if there's a pattern that we can recognize. So x squared. And I think in this case, because it has this cyclic pattern, it'll just cycle through these values 0, 1, 0, negative 1 to get all the derivatives of higher orders. Then we can just recognize the basic pattern that it's forming here, just going up to maybe the first few terms here. This should be x to the 4th, this would be x to the 5th. Okay, so let's write out what it would be there. So we know sine of 0 is 0, so this term is 0. And notice that all the ones that have even powers will be 0. right? And also same with the fourth derivative, that will be the same as sine of 0. Sixth derivative would be the same as negative sine of 0, and so on. So we're just left with these odd power terms. And of those odd power terms that remain, they're going to alternate between 1 and negative 1. So it'll be positive x here, then minus 1 over 3 factorial x cubed, and then plus 1 over 5 factorial x to the 5th. And we can guess that, yeah, it's just going to cycle back and forth between 1 and negative 1 on all the odd degree terms. So I have 1 minus 1 over 7 factorial x to the 7th, and so on. 1 over 9 factorial x to the 9. Okay, so for sine x, it's going to just be all these odd degree terms. So one way we can write this it starts with x equals 1 here, and it's positive for the first one, so here I'll have negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, going from n equals 0 to infinity. So I'm using 2n plus 1 because that'll give me all the odd power terms. Now, to show that sine x is equal to its power series for all x, well, let's look at the Taylor's theorem for Rn here. So again, here we know that Rn of x is going to be less than or equal to m over n plus 1 factorial x to the n plus 1, where here m again is a bound on the n plus 1th derivative, for x that are less than or equal to some d. And the nice thing is now with sine and cosine, they have a very easy antiderivative. So this is, they have a very easy upper bound. So this, when we continue through various derivatives of sine, they're all either going to be absolute value of sine or absolute value of cosine. Right, some plus or minus version of that, but when I take the absolute values, they're always going to be positive. And we notice that these are always going to be less than or equal to 1 for any x. So here I can use m equals 1, and that'll work really well for this particular case. And there we have that the limit as n goes to infinity of the absolute value of Rn of x will be less than or equal to the limit as n goes to infinity of 1 for m, so 1 times x to the n plus 1 over n plus 1 factorial, which we know this goes to 0. So therefore we've shown that as n goes to infinity, Rn of x goes to 0. And hence that shows that sine x is going to converge to the values of the sum of its series.